Our next talk is the current state and future of Rust compiler performance. That's a big one, right? Unfortunately, Sparrow couldn't be here in person because of visa issues, so this is a recorded talk. So please still give a massive hand to Sparrow and enjoy the talk.
Hello everyone, I'm Sparrow Li. It's a pity that I can't attend the conference in person. Thanks to the organizers for giving me the opportunity to share and communication with so many great Rust fans. As the title suggests, the topic of my sharing this time is the current state and the future of Rust compiler performance. As Rust is used more and more widely in the industry, more and more large-scale projects with millions of lines of code are being developed. So compilation efficiency has become an important consideration. Today, I will introduce to you the efforts made by the Rust community to improve compilation efficiency so that everyone can have confidence in Rust's compilation efficiency. At the same time, many means will also be helpful for improving the performance of daily projects. I also hope that more people can participate in the Rust community's work to improve the compiler performance. So this is my personal introduction. I worked at Huawei and have been contributing to the Rust community since 2021. I started with SIMD library stdarc and then to the Rust compiler and participated in the work of the parallel Rust-C working group at the end of 2022. When it comes to the compiler time, Rust is not outstanding compared to some typical fast prototyping languages such as Python and Go. Just like a classical debate, which is more valuable, programmer time or CPU time? It is obvious that Rust has done a lot of complex work in compiler to make it easier to write high safety and high performance programs. Monomorphization, type checking, borrow checking, macro expansion, optimization, and so on. So when first time you use these features, you will say, wow, this is cool. But as a developer of a large project, when you can only run handful builds a day, you may think that it will be much better if this language could compile fast. Of course, just like the comics, this may be a good chance to be lazy though. So how slow is Rust's compilation? Let's look at the pictures on the left, which compares the trait of compilation time growth as the increase of functions for various common languages. It may be a little hard to distinguish them all, but you just need to know that the step test two lines, they are Rust. The right one compares the compilation time of Rust and C++ for the same number of functions in two scenarios, for compilation and incremental compilation. As you can see, Rust has no disadvantages when the amount of code is small. But as the project grows bigger, Rust's compilation time will inflate faster. Wow. So in recent years, improving compilation performance have become a key task for the whole community. In fact, during dozens of releases this year, the performance of the Rust compiler has more than doubled. This relies on the amazing efforts of all contributors, especially the compiler for performance working group, which has developed many automated tools such as RustC Perf to measure, monitor, and optimize the performance of Rust compiler. And they also help contributors locate the impact of their PRs on compilation time. Besides, there is the parallel RustC working group in which I participate in. which is responsible for the implementation of this roadmap feature. It can now be used in Netlib builds, which can improve the compilation performance by about 30% in average, and is expected to land in stable versions before next year. Currently, the community has many tools to improve compiler performance, such as profile gold optimization, which we call PGO. As we say, experience is the best teacher. Rust programs support secondary optimization based on the various data collected by the compiler in the first compilation, such as inline, layout, and memory allocation, to improve performance. And the Rust itself can certainly do the same. Thanks to the great efforts of the Rust Performance Working Group, we can now optimize the Rust-C's performance through PGO on Linux and Windows, which have 10 to 20% improve in average, which is an exciting result. And the binary optimization ways, such as both binary optimization and layout tool, and link time optimization, are amazing optimization methods that rearrange the Rust-C binary. We can already benefit from these technologies on Linux and from more involvement in the visible feature. And we have also made some progress on one thing that often expands the time of the compilation, that is linking. This year, the LLD linker has replaced the GCC linker as the default choice on Linux, which means that link time can be reduced to a reflection of the previous ones, reduce the overall completion time up to 40%, which is an amazing achievement. And compared to external tools, most of the work is actually done in the optimizations of Rust itself. In the past dozens versions, Rust-C has done a huge amount of optimization work. For example, lazy calculation of immediate data, use of fast hashes, reduce the size of AST, and space bitmaps, and so on. Here is a very interesting example. In the early years of syntax tree token optimization, a PR only changed 3 lines of code, which reduced the redundant conversion in token structures, which can improve the overall performance of Rust-C up to 5%. I can only say that this is an inspiring change. Optimizations of Rust-C happen every day. It is the accumulation of small things makes the performance of the Rust compiler steadily improve. However, code-level optimizations requires a deep understanding of the whole compiler, and as time goes by, it becomes more difficult to find optimizations with good cost effectiveness. So the community hopes to make changes in the overall design, and parallelization is an attractive solution. Cargo's parallelization was the first solution proposed and implemented. And shown in this picture, multi-threads with no dependencies can be compiled in parallel. However, as can be seen from the picture, only about half of the time has highly CPU uses. In the second half, the completion of a few large-scale grids greatly extends the entire completion time. This also inspires us that there is a lot of room for parallelization within a single grid. The following figure shows that the thread condition when they compile a grid. In fact, we have already completed some parallelization in there. The compiler is divided into the front end and the back end. The front end is responsible for generating various LLVM ARs, while the back end is responsible for generating binaries, optimization, and linking. Just like when producing a toy, the front end is responsible for designing the toy's arms, legs, body, and other parts, while the back end will process, study, and assemble the various parts. The back end process has been parallelized, which means that we can process multiple parts at the same time and assemble them. The more parts we divide, the higher the efficiency of parallelization. But unfortunately, the front end, that is the design process of the parts, is still single-threaded. The close connection between companies makes this not an easy task. But the community still has ambitions for this, which is why the Parallel RustC working group was established. This project was first proposed by team members in 2018, and a working group was established in 2019, which completed the essential implementation of this feature. But then there were some technical blocks which put the development of this feature on hold. Until 2022, where a lot of technical exploration, we finally solved the blockage, rebuilt the working group. It has been landed in nightly versions at the end of 2023, with an average performance improvement of about 30%, and is planned to enter the stable versions at the end of this year. So next, I will introduce some more detailed design in front-end parallelization. I believe that many scenarios are also inspiring for our daily development. This picture shows the general process of the Rust compiler. The red part is where the main work of front-end parallelization. We have implemented parallelization on the data structures and iterative APIs used in many compilation processes, as well as the core system of the compiler. It makes most compiler developers almost unaware of the extent of the parallelization. This is exactly what we call abstraction or encapsulation. The difficulty of this work, which was also the technical blockage before, was the performance loss caused by switching from a single-threaded environment to a multi-threaded environment. We had to replace a large number of efficiency data structures such as RIF cell to mutex, which would result in an overall performance loss of about 10 to 30% and single threading. It's just like replacing all roads in the city with railways in order to use faster trains. Then people who are used to cars can only drive on railways, which is difficult to accept, especially since we haven't proved that the parallel front end, that is the train, can show safety and stable performance advantages. So we redesigned the data structure used by the compiler to include both efficiency non-threaded and inefficient thread-safe data structures, and automatically use the appropriate synchronizer according to the compilation environment, just like a car that can be transformed to travel on both roads and railways. After a lot of optimization work, this design reduces the performance loss and the single thread from to 1 to 3%, which is amazing. In order to ensure that this new design can be used safely and will not affect other compiler developers, we also have make a new thread safety check mechanism and ensure that the data centralization mode is consistent with the overall environment. In other words, at the same time, there will be only railways or only roads in the city. And on the other hand, some important components of the compiler also need to adapt to the parallel environment, such as the memory allocator. In multi-thread environment, memory allocation requires from different threads and will cause the global allocator to be overloaded. Imagine that if there is only one Starbucks in multi-pack blocks, then this Starbucks will be crowded with a large number of customers every morning. So the best solution is to open a branch Starbucks in each block. The multi-threaded memory allocator follows this idea and assigns a resource pool in each thread, ensuring that there is no competition between threads, which greatly improves the performance. However, this method is not general, such as the cancel of chorus results in the compiler. These chorus may be accessed from any thread and requires a unified storage. We can also imagine that a popular sport needs to keep the backpacks of tourists. Tourists need a unified storage too. The best way is to expand the scale of the storage and then classify tourists' backpacks according to their ticket numbers. It is same in parallel compilation. In order to improve cache efficiency, the data will be stored in a different hash table during the hash value of each access key. And there is a 33 times redundancy compared to the single thread. Since the original cache is a hash table, there is no need to recalculate the hash value. So this is an amazing effective design. Of course, there is still room for improvement. With the number of threads increase, for example, from 8 to 16, the data computation in the same compilation will also increase, resulting in the performance of 16 threads to be even lower than 8 threads. And some compilation process, such as macro expansion and HAR lowering, can still be only compared with a single thread. And the parallel front-end shelving scheme based on work stealing also leads to deadlock problems. When work stealing introduces additional data dependencies, deadlocks may sometimes occur. The current solution is to adjust the code logic to avoid extra dependencies. However, it is still a big challenge for us to completely solve the deadlock problem without reducing the whole performance. In addition to the various solutions I introduced earlier, Rust compilation performance has a shining future. For example, the current linker still has a huge room for improvement. The community is working hard to make LLD, mode, and other linkers which are dozens of times faster than the GCC linker, the default choice for users. And using thin LTO instead of full LTO by default may be a more cost-effective solution. We can't forget the incremental compilation. Currently, Rust's incremental compilation is still far behind C++. The The compilers lacks fishing, macro expansion, and the other parts don't support incremental explanation. And the existing parts also have a lot of redundant compilation. For example, the change of the source code location span will cause a large number of compilation processes to need to be compiled. Let's be more ambitious and imagine some cooler ideas. Currently, Rust projects are compiled in crates, and sometimes there are repeated compilation tasks between crates, such as type checking for the same trait. If we can share in this immediate data compilation data, it can also save a lot of compilation time. And when it comes to project compilation, currently Rust projects management is based on downloading and comparing source code. The compiler also generates a Unicode hash value for each binary, which often requires recompiling the source code in various environments. Perhaps this solution can be more ambitious, such as compiling a binary that can be shared in various environments. This may require improvements in both Cargo and Rust-C. And we can even think about whether the compiler can be refactored. The current compilation is based on crate granularity, and all compilation immediate data is stored in a data structure called global context. Can we get rid of this solution, such as using smaller granularity, such as in modules, to reduce a lot of data computation in crate compilation? This is a question that deserves a lot of in-depth thinking. So the above is my sharing on the current state of and the future of Rust compiler performance. I would like to thank the organizer again for providing the opportunity to me. I really hope that I can have the opportunity to come to the conference in person next time. Thank you for coming. Thank you.